Hello guys, welcome to tutorial 9 for the Introduction to Communication Networks course. Earlier in this course we discussed what's a network, what does a network consist of, the network performance and the factors affecting the network performance like the throughput and the delay. And then we started discussing the internet protocol stack starting from the application layer.
The application layer, and then we went through the transport layer. Today we'll be discussing the network layer, and we said we have also the data link layer and the physical layer. In the application layer, we discussed one of the protocols implemented in the application layer, which is HTTP. In the transport layer, we discussed two of the protocols implemented in the transport layer, which are UDP as well as TCP. And last time we mentioned the last part of TCP. We mentioned the differences between UDP and TCP, where the UDP needs or has no rules or limitations, but the TCP is connection oriented, allows reliable delivery as well as flow control and congestion control. We discussed how it allows the flow control and the congestion control in the past tutorial through adjusting the congestion window as well as the receiver window. Today we'll be discussing the third layer, which is the network layer. Okay. As we're used to, we'll go through some of the terminologies we'll be using throughout this tutorial. First, we'll be mentioning datagram. What is the datagram? If you recall, when we first started discussing the Internet Protocol stack, we mentioned that initially in the application layer, there is a message, added to it a header, it becomes a segment, added to it the header at the network layer, it becomes the datagram. So the datagram, the segment, when it's encapsulated, it becomes a datagram. What was the encapsulation process? It was the process of adding headers at each level of the protocol stack, Internet Protocol stack. Okay, today, while discussing the network layer, let's first start by mentioning the main functionalities we'll be discussing for the network layer. The network layer is responsible for forwarding as well as for routing. What is the main differences between forwarding and routing? Well, forwarding is mainly going from one place to another, from one hop to another. So the network layer is responsible to know where is the packet is going to go from one place to another. So from one hop to another is the forwarding, while on the other hand, the routing is the whole path. So let's give an example. If A is sending a packet to D through B and then C. So A will send to B, and then B will send to C, and then C will send to D. Forwarding is the principle of A sending to B from one hop to another, or from B to C, from C to D. But the routing is all about the path, the ongoing path from A till D. Okay. Another term we'll be using is the maximum transmission unit, MTU. What is the maximum transmission unit? Well, each network has a maximum allowable packet size it can handle. So within each network, for each network, so for each network has its own maximum transmission unit. A capacity where you can a maximum size for the packet that could be sent on this network. So again, what is the maximum transmission unit? It's simply the maximum allowable packet size a network can handle. It can differ from one network to another. So a packet, on a side note, the datagram is also the packet size. Okay, so let's go back again to the maximum transmission unit. So if we said that the maximum transmission unit of a certain network, okay, is a certain capacity, then let's also mention another thing that we will need during the solving the practice assignment. Another terminology we'll be using, the maximum segment size. And I'll mention right now the difference between the maximum transmission unit and the maximum segment size. The maximum segment size is actually determined at the transport layer and shouldn't exceed the MTU, the maximum transmission unit. Okay, let's take it step by step. We just mentioned that the maximum transmission unit is the maximum allowable packet size a network can handle. Okay, if we're having a packet size, or the maximum size a network can handle is a certain maximum transmission unit. This should include the maximum segment size as well as the headers. What was the headers? The headers added at each layer. At the transport layer, at the network layer, and so on. So the maximum transmission unit should be greater than or equal the summation of the maximum segment size plus, of the maximum segment size and the summation of all headers. Should be greater than or equal the maximum segment size plus the summation of the headers. Okay. So the maximum segment size is determined at the transport layer and shouldn't exceed the maximum transmission unit. What was a segment? We just mentioned at the beginning of the tutorial, the segment was simply the message added to it, the transport layer header. So when the segment is added, another header is added to it to become a datagram. So the maximum transmission unit, the datagram, we just mentioned that the datagram is the packet size. So the packet size that is allowed within a certain network is the maximum transmission unit, should be greater than or equal the maximum segment size added to it all the headers. Okay, what if I'm sending a file, okay, or a packet, or I'm sending a whatsoever a file that is greater than the maximum transmission unit afforded by this network? So let's assume I'm sending a file of size whatsoever 2000. Okay, I should put into consideration that this file should be, while transferring this file through a network, I should check the maximum transmission unit of this network. What is the maximum allowable size for a packet to be transferred on this network? After checking the maximum transmission unit allowed on this network, I could now fragment the file I'm having. So this brings us to a new terminology, which is the fragmentation. It's cutting to pieces the things I'm sending to fit the maximum transmission unit of a certain network. So to fit the maximum transmission unit of each network, I could simply fragment what I'm sending. So if I'm sending 2000 size of file of size 2000, I should simply fragment the size according to the maximum transmission unit of a network. So the fragmentation, two things we need to know in the fragmentation is that each fragment would get its own header and would be sent independently. Also, if one fragment is lost, the whole file should be retransmitted. Okay. I hope you do get the idea of the fragmentation right now. Also, we need to know the terminology or the term fragment offset. What is the use of a fragment offset? Well, the fragment offset is used to order the fragments. Okay. So if I just mentioned that I have a file of size 2000, for example, I'll be fragmenting this file into 4 fragments. So I'll be having fragment 1, 2, 3, and 4. Okay? In real life, well, it's not divided to 1, 2, 3, 4. Well, we have something called a fragment offset. Okay? Which helps us to order the fragment. What is the fragment offset? It counts the total shift from the beginning of the file. And is always a multiple of 8. Okay, so for this example, if we're having a 2000, if we're fragmenting to 4 fragments, so I'll be starting with an offset of 0, and then I'll check, can I have a fragment of size 500? Is 500 divisible by 8? No, it's not. So I'll see what is the least number that is divisible by 8 before 500. So if 498 divisible by 8? No, it's not. So let's try. Is 496 divisible by 8? Yes, it is. So I'll be having an extra fragment. So this fragment will contain the first 496 bytes or bits. Okay? If this fragment contains the first 496 bits, then the offset, the total shift from the beginning is what? Is 496. divided 8, so the offset of the second fragment would be 62. How would I get the offset of the third fragment? 496 plus 496. So we'll do just 496 plus 496. It's 992. Divided 8, the total shift by 8. So the offset of the third fragment is 124. And so on and so forth. Okay. Also, we need to know the term more fragments flag. We have a term called more fragments flag, which is added to the header of each fragment. What does it help us to know? It's just set to 1 to all fragments, but the last one, which is set to 0. Which is an indicator to indicate that this is the last fragment of the packet. So let's have it by an example. If we're having a packet of size, the same packet we're sending of size 2000. Of size 2000. Okay. I'll be setting, and I divided them to 5 fragments. I fragmented the packet into 5 fragments. The first one was 0, the second one has an offset of 62, and so on. So I fragmented it to 5 fragments. Okay. Each was of size 496, but the last one, if you added 496, on a side note, if you added 496 times 4, it would be 1984. So the 5th fragment will have the size of, I'm just calculating it right now, 16. Okay, if you just, I know the doctor already mentioned that in the lecture, but on a side note, why are we only allowing the fragmentation to be a multiple of 8? Because the offset, as we said, is a multiple of 8. So why didn't I leave the first fragment to be 500? Because 500 is not divisible by 8. So I should find the nearest number, which is divisible by 8. So the nearest number to 500, which is divisible by 8, is 496. That's why I mentioned that 496 would be the size of each fragment. And how did I get the offset? I simply divided the 496 by 8. And for the second fragment, for the third fragment, how did I get the offset? I had 496 plus 496, the total shift from the beginning. So I had 2 shifts, 496 plus 496, divided 8. So all the fragments should be divisible by 8, but the last one, I don't care if it's divisible by 8 or not. It's just the remainder. As I get the offset of the last fragment from the ones before it, not the ones after. So I don't need it to be divisible by 8. Simply, the last one would be 496 plus 496 plus 496 plus 496 divided by 8. This would get the fragment offset of the last fragment. So I don't need it to be, I don't need the data in it to be divisible by 8, as I already get the offset from the data from the previous fragments. Okay, this was a side note. Let's go back to, I'm just making sure that you got the idea of the fragment offset. Let's go back to the more fragments flag. Well, if we, in the same example, if we have a packet of size 2000 and we're dividing it into five fragments, the first fragment, in the more fragments flag, it would be set to 1. Is there any more fragments? Yes. In 2, is there any more fragments? Yes. In 3, is there any more fragments? Yes as well. In 4, is there any more fragments? Yes, we're having 5. But in 5 is the last fragment, so the more fragment flag for the last fragment is set to 0. This is an indication that fragment number 5 is the last fragment in this packet. Okay. Let's go to another thing, which is the IP addresses. As we mentioned earlier, in the application layer, we discussed the HTTP. In the transport layer, we discussed UDP and TCP. In the network layer, we'll be discussing the IP protocol, as well as different routing protocols. So, in the network layer, we said the main functionality of a network layer is to do the routing, the forwarding and the routing. So, how is the forwarding and the routing, or what is included in the forwarding and the routing? And the routing is the IP addresses. So, in IP addresses, we have IP addresses version 4, which are of size 32 bits. Okay. On a side note, there's also a version 6 of 64 bits, of a size of 64 bits. Okay. It's 30, so IP version 4 is 32 bits. Also, any IP, if you recall last tutorial, I mentioned that any IP is globally unique. So the IP is globally unique. It's assigned to interfaces you use to run internet not devices. Okay. Also, you need to know that the IP addresses consists of 2 parts, or the 32 bits are divided upon 2 parts. The network address part okay, and the local part, where the local part includes the subnet part as well as the host part. Let's give an example about the IP addresses to make it more clear. So we said that the IP addresses are 32 bits. So if we're having the 32 bits, 0, 1, 2, 3, 4, let's start it from the beginning so that we have enough space. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and so on until bit 31, from 0 to 31. Okay. I can say that I will divide the IP address part, that anyone within the same network will have the same 8 bits in common, for example. So how many bits are remaining? If we have 32 minus 8, 8 is for the network address part. What is the network address part? It's the part where anyone within the same network should have in common. So for example, if the network address part for it's مثلا 101 to 011 okay, so if this is the network address for network A, for example, anyone within network A should have the same 8 bits of network address port. Okay, what about the remaining bits? If we have, subtracted 32 minus 8, we'll be having 24 bits remaining. The 24 bits remaining are divided upon the subnetworks, and I'll mention right now what is a subnetwork, and the host part. So we can say that the subnetwork will have another 8. So anyone within the same subnetwork will have in common not only 8 bits, but the 8 and the 8 in the network. You'll get the idea when I mention what is a subnetwork later on. Okay, so what the remaining bits for the host part would be 24 minus the 8, it will be 16 bits. Okay, let's have an example for that. Let's assume we're having network. A network is called A, and another network which is called B. And within A, there are subnetworks which are called X and Y. Okay, what will X have in common with Y? Well, if we said like the last example, if we have the network part, if in the division of the IP address, if we said that we'll be giving the network address part 8 bits, for example, and the local part, which is divided into the subnetwork and the hosts. So what will X and Y have in common? X and Y are within the same network, so they will have the first 8 bits in common. So the first 8 bits will be in common within X and Y. Okay, if within X there are 2 hosts called F and E. What will F and E have in common? F and E will have in common the first 16 bits in common, as they belong to network A and subnetwork X. So they will have the first 16 bits in common. What will differ? The remaining 16 bits. I hope you already get this part. The doctor already mentioned it in the lecture, but I thought of repeating that. The last terms I need to discuss, the term subnetwork. I already mentioned the subnetwork, but I'll go through it again. What is a subnet or a subnetwork? It's a small network where all devices have the same network address ports. So like the last example, if you're having a network A and network B, A had X and Y as subnetworks. Within X had 2 hosts, F and E. What was common within F and E, as they are within the subnetwork hosts F and E, which were part of the subnetwork X, what did they have in common? The network address port as well as the subnet part. What about X and Y? Subnets X and Y. What did they have in common? What did they have in common was the only the network address port, where X and Y belong to network A. Okay. One more thing to discuss is the subnet mask. What is the subnet mask? It's the number of bits. Sorry. In network address port. And I'd highly appreciate if you go to the lecture slides, you'd get the network part. For the subnet mask is represented in ones, while the host part is represented in zeros.
Okay, going to problem 1, the practice assignment. Suppose that a TCP segment that contains 2048 bytes of data plus 20 bytes of TCP header is passed to IP for delivery across two networks of the internet, N1 and N2. So the data will pass through two different networks N1 and N2. The two networks are N1 and N2. The network N1 uses 14 bytes of header for its data link layer frames and has a maximum transmission unit. The MTU is the maximum transmission unit of 1024 bytes. The network N2 uses 8 bytes header with a maximum transmission unit of 512 bytes. Okay, let's have a table or draw a table having this information that he just gave us in the question. Starting with the network name, we have two networks. So we're having network N1 and network N2. The total the maximum transmission unit in each one of them. In N1, the maximum transmission unit is 1024. In N2, the maximum transmission unit is 512. The data link layer header that will be added in each one of them. In N1, it uses 14 bytes for the data link layer header, and in N2, it uses 8 bytes for the data link layer header. As for the IP header, we'll know the size of the IP header when we complete reading the question. Each network's maximum transmission units gives the total size including the packet's IP header and the data link layer header. Give the size and the offset of all sequence of fragments delivered to the IP layer at the destination host. Assume all IP address or all IP headers are 20 bytes long. So the IP header, whether in N1 or N2, should have a size of 20 bytes. Okay. So the remaining bytes we'll be having for the data, we could get them by simply subtracting the headers from the maximum transmission unit that could be transmitted within a certain network. So the remaining bytes for this network N1, the remaining bytes and for N1, we'll subtract the 14 and the 20, which are the data link header and the IP header, from the maximum transmission unit. So the maximum or the bytes remaining for a segment, remaining bytes for a segment, or over here would be 990, and in N2 would be 484. Again, how did we get these numbers? We simply subtracted the headers from the maximum transmission unit. So the remaining bytes could be used for this, that could be used for the segment is 990 for N1 and 484 for N2. Okay, as we already mentioned, since the offset should be a multiple of 8, so a number that is a multiple of 8, so I should get the remaining bytes for the segment that could be divisible by 8, that is divisible by 8. So the nearest number from the remaining bytes for the segment that is divisible by 8 over here is 984. And the nearest number over here that could be assigned for the segment size that is divisible by 8 is 480. Okay, so this is in this section or this column, we're having the remaining bytes that are divisible by 8. Okay, I just redrew the table so it would be more clear. So again, what we did, we just wrote the given in the problem. He said that we're having two networks, N1 and N2, N1 with a maximum transmission unit of 1024 bytes, and N2 with a maximum transmission unit of 512 bytes. The data link header that will be added in N1 is of 14 bytes of size, and in N2 it will be of 8 bytes of size. And finally he said that all IP headers that will be added, whether in N1 or N2, will be of 20 bytes long, so they're both 20 bytes. What we did is that we calculated the remaining bytes we could use for the segment size. So we subtracted both headers from the maximum transmission unit. So we got these bytes as the remaining bytes that could be used for the segment. And as we already mentioned before, the offset or the segment size, so that we could have an F offset as a multiple of 8. So the segment size should be a number, or the bytes should be a number which is divisible by 8. So we got the nearest number which is divisible by 8 that we could use as the segment size in each network. Afterwards, we should continue with the process where the data is sent from this network to this network. Okay, starting with the process, let's go again to the problem. It said that a TCP segment that contains, so the TCP segment that we will be transferring is of size 2048 bytes plus the 20 bytes of the TCP header. So the segment we want to transfer, or that will travel through networks N1 and N2, is of size 2048 bytes of data plus 20 bytes, which are the 20 bytes needed for the TCP header. So in total, we're having a segment of size 2068 bytes, which is passed to IP for delivery across two networks of the internet. So this segment of size 2068 bytes would pass through both networks N1 and N2. Initially it will pass through N1. So let's go through the process where this segment passes through N1. Since the size or the TCP segment is of size 2068 bytes, hence, we need to fragment it into further fragments or smaller fragments, as the maximum transmission units that N1 can afford is 1024. So now we need to fragment these 2068 bytes in order to transfer it through network N1. So we'll simply divide these 2068 bytes into smaller parts that could be transferred into network N1. So first we'll be having the fragment. Let's have another table having the fragment number, and then the segment bytes that this fragment will have, and the offset, as well as the more fragments flag. Why did I include these columns? As in the question, he asked for, after mentioning all the givens, he asked for he said that each network's maximum transmission units gives the total size including the packet's IP header and data link header, give the size and the offset of the sequence of fragments delivered to the IP layer at the destination host. So he needs to know each fragment is of what size and the offset of each segment or each fragment. What we added over here is the more fragments flag. We just added it as an extra column. It wasn't required in the question itself. So initially we have the 2068 bytes. If each time we transfer, we can have only 984 bytes for the segment. So the first segment will be having 984 bytes, which is the maximum allowed bytes for a segment that could be transferred through N1. So the segment bytes are 984 in the first fragment. The offset, how can we get the offset? Initially the offset is 0. Then the more fragments flag is an indication. Are there any more fragments for this packet? Yes, it will be further fragmented, so it would be set to 1. Then another fragment of size 984. This time, how can we get the offset? Simply we see how many bytes have been transferred so far and divide them by 8. So 984 divided by 8, I would get a 123 of an offset as an offset. Are we done yet? Okay, let's subtract the 2068. Let's subtract the 984, the first fragment we just sent, and the other fragment. We'll have as a remaining 100 bytes. So we need another fragment 3, which contains 100 bytes of data, or 100 bytes for segment bytes. The offset for these, or for this fragment, would be the previous bytes sent divided 8. So 984 plus 984 divided 8, we get 246 as an offset. We forgot to write the more fragments flag in the previous fragment, so it would be 1. In the last fragment, it would be 0. So for network N1, the segment which contained 2068 bytes will be fragmented into 3 fragments. How did we get the number of fragments that that this segment needs to be fragmented? Simply you can divide it by the maximum allowed size for the segment. You would get, if we divided 2068 by the maximum size that could be allowed for a segment, which is 984. So 2068 divided 984 would get 2.1. Since there is nothing called as 2.1 fragments, this means we need 3 fragments. We just round up the 2068 divided the 984, which is the maximum allowed size for the segment within N1, any segment within N1, would give us a 2.1. So we need to round up. We'll be having 3 fragments. We're always rounding up. We're having the ceiling, as there is nothing called an 0.1 fragment, so we'll be rounding up. We need 3 fragments. The first fragment will be the maximum allowed size, which is 984, and the second fragment will also have the maximum allowed size of 984, which gives us a remaining of 100 bytes. And how did we get the offset? We simply we start the offset by 0, and then we calculate the offset by calculating how many bytes have been transmitted so far divided 8. So for the second fragment, how many bytes were transmitted so far? It was just 984 bytes divided 8. It will give us a 123. And for the third fragment, we added up the 984 plus the 984 divided 8. It will give us a 246 offset. As for the more fragments flag, we set the more fragments flag to 1 in all fragments but the last one. So Do we have more fragments? Yes. Do we have more fragments? Yes. In the last fragment, we're having no more fragments. Let's go to the what will happen further next in N2. So now, initially, we had 2068 bytes segment, which was transferred into N1 into 3 fragments. The first one had a size of 984, the other one had a size of 984, and the third one had a total size of 100 bytes as a segment size. But the maximum transmission unit was 1024, and for N2, the maximum transmission unit was 512. So if we added up the headers to these numbers, will end up to the maximum transmission unit. So if we added the network layer header and the data link layer header, which is 20 and 14, we'll get a sum of okay, I just redrew the table again so that we could have the rest of the answer over here. So what we did so far was that we saw the maximum segment size which was transferred, which was of size 2048 bytes of data plus the TCP header, which is 20 bytes. So in order for this segment to pass through N1, we had to fragment it into 3 fragments. The first fragment was a fragment of size 984. The second one was of size 984, and the last one was of size 100. So now we need these fragments to pass through N2, which has a maximum transmission unit of 512, and the maximum segment size that could be allowed is 480. So now we need to further fragment these fragments so they could pass through N2 as well. So let's start with the first fragment, which is fragment which is the first fragment in N1, which is the first fragment N1 fragmented. So here we'll be having a table for the same table, exact table. We'll be having a fragment number, a further fragmentation, cell, and segment bytes, offset, and MF flag. So the first fragment was of size 984, and the maximum segment size N2 could allow is 480. So I now need to know how many segments can I further fragment this fragment into. So I'll simply divide the 984 divided the 480. The 984 divided the 480, it will give us a 2.05. So that means we need three more further fragmentation. So this fragment will be fragmented into 3 fragments in order to pass through N2. The same fragment will be further fragmented into 3 more fragments. The first one will have the full capacity or the full size, which is 480. The second one will also have the full size, which is 480. And the last one will have the remaining bytes. How to get the remaining bytes? We simply subtract the 480 plus the 480 from the 984, which was the total size, would have a remaining of 24 bytes. How can we get the offset? The offset for the first one should be 0. For the second one should be the bytes, which was all the bytes which was sent already, which are 480 bytes divided 8, sorry. So 480 divided 8 will have an offset of 60. Then to get the offset of the third fragment in the third fragment, which was further fragmented in fragment 1, We'll get it by adding the 480 plus the 480 divided 8. We'll get a 120 offset. Here, the more fragments flag in the first fragment will be 1, in the second fragment will be 1, and in the third fragment as well will be 1, as we have more fragments to fragment. Going to the second fragment, how many fragments that the second fragment would need? How can we get it? We'd simply divide the 984 divided the 480, which we just did, to give us 2 point something. So we need 3 more fragments, or to further fragment this fragment into 3 more fragments. Each, the first will have 480, the second will have 480, the third will have the remaining, which is 24. How can we get the offset? All the bytes that have been sent before divided 8, so 480 plus 480 plus 24 divided 8 will get a 123 offset. Then to continue, we'll have the offset of this one by adding all the bytes before it divided 8. So all these bytes divided 8, it will give us an offset of 183. And to get the offset of the last fragment in last further fragmented fragment in fragment 2, we'll add up all the numbers before it divided 8. We'll get an offset of 243. As for the more fragments flag, it will be set to 1 to all of them, since we're still having a further fragment that will be sent. So as for fragment 3, does fragment 3 need to be further fragmented? No, it doesn't need to be further fragmented, as it's of size 100, and the bytes, the maximum segment size that could be sent in N2 is 480, so I don't need to further fragment the third fragment. So here I don't need any kind of further fragmentation, so the segment bytes will be 246 as is. And how to get the offset? We simply add up all the bytes that have been sent before divided 8. We'd get an offset of 246. Finally, in this fragment, the more fragment flags will be set to 0, as we're having no more fragments for this file. This is all the file that is sent.
Just a small note, while solving the last part, we said that the third fragment would be having segment bytes 246. That was a mistake. I meant an offset of 246, but the segment bytes would be 100 as is. So here we're having segment bytes 100, not 246. Thank you.
That is all about problem 1. I hope you got the idea behind it. We'll complete answering the rest of the questions in the tutorial. Wish you all the best. Good luck.